Okay, so far in our lectures on linear elastic finite element analyses, we've basically gone through the entire process of constructing the element equations through assembly, through applying the boundary conditions, and then solving them just by saying we can invert that matrix to solve. We didn't spend a great deal of time on the matrix inversion. But what that gives us when we finally solve is we get the nodal displacements and the reaction forces at the nodes. So let's suppose that we've got to that point. Okay, so suppose we've solved for the displacement and the reaction forces, displacements at the nodes rather, and nodal reaction forces, right? By solving the equation that looked like K, this is in the static case, right, times U, the nodal displacements, is equal to the nodal forces vector F. Okay, so the question now, okay, so we've got the nodal displacement and the reaction forces. How do we get stresses and strains? Okay, so recall that stress and strain are field variables, right? And what that means is that they depend on the spatial variable x. Okay? And of course, displacement is that as well, but we have an entire field. So we've got to start talking a little bit about where are we going to report the stresses? What exactly are we reporting? And is that the quantity that we care about wherever we do report it? Okay? So let's begin just by say that we're going to use the small strain displacement relationship. So for small strain, we're going to use the strain displacement relationship as follows. Okay, and that strain displacement relationship looked like epsilon ij was equal to 1/2 times ui comma j plus uj comma I, right? We'll call that equation 1. And then we're going to substitute now our approximations for u, right? So substitute the approximation for u, right? Namely that we have this quantity, call it u star, and I'll put a sub I there, is going to be equal to the quantity n transpose, where this is our vector of interpolation functions, times the nodal displacements ui epsilon, right? Presumably we know these nodal displacements now because we just solved for them. So we're going to try to use those now. Okay? So if we substitute this in, we end up with the following. We say epsilon ij is going to be equal to 1/2. Now we have inside the parentheses here, we have n comma j transpose times u e I, right? And then plus n comma I transpose times u e j, right? Let's call that equation 2. So what do you instantly notice? These derivatives, just like they were when they were inside the integrand, these derivatives are with respect to x1, x2, x3, right? Not with respect to xi, eta, and zeta. And the interpolation functions n are functions of xi, eta, and zeta, right? So let me write that down. So recall the interpolation functions n are going to be functions of xi, eta, and zeta, right? Not x1, x2, and x3. So what that means is that we need to use the mapping that we developed previously. Okay, and let me remind you of that mapping. Okay, the mapping said, if you remember back to that lecture, that we could write the partial of n with respect to x1, partial of n with respect to x2, and the partial of n with respect to x3. So that quantity is equal to, and we had this this term that we called j star, right, times the quantity partial of n with respect to c, partial of n with respect to eta, and the partial of n with respect to zeta, right? So call that equation 3, where what? Where we know that we define j star as equal to the inverse of the Jacobian matrix, right? Call that equation 4. And we define the Jacobian as follows. We said that the Jacobian was equal to the following, was equal to the partial of n with respect to c, that quantity transpose, partial of n with respect to eta transpose, and the partial of n with respect to zeta transpose. Okay, times the quantity, these are the x values now, the nodal coordinates, x1 of the element, x2 of the element, and finally x3 of the element. Let's call that equation 5. Okay, so using this mapping, let's go through just a couple terms in the strain. I'm not going to write all 6 of them out, but so using this mapping, we may write the following. So let's take epsilon 1 as an example. That is going to be n, comma 1 transpose times u of the element in the one direction, okay? And if we expand out using our mapping for n transpose, the partial of n with respect to x1, then this quantity, this n transpose term, becomes j11 star, right, times the partial of n with respect to c transpose plus j12 star times the partial of n transpose with respect to eta plus j13 star partial of n transpose with respect to zeta, right? So that's just plugging it in, times this u1 of the element. Okay? So that's one example. How about epsilon 1, 2? So we'll do one normal and one shear. So for epsilon 1, 2, that looks like 1/2 now times the quantity n comma 2 transpose times u1 of the element plus n comma 1 transpose times u2 of the element, right? And if we start expanding that out using our mapping, this looks like 1/2. Now I'm going to put a big bracket here for us. This first term that I'm going to look at here is this n partial n with respect to x2, and this becomes now j21 star times the partial of n transpose with respect to c plus j22 star with the partial of n transpose with respect to eta plus j23 star partial of n transpose with respect to zeta. Okay, this whole thing needs to be multiplied by the nodal displacements u1e, right? And then so that's this first term. The second term is then plus and now we do it again, except for this term looks like J11 star times the partial of n transpose with respect to Xc plus J12 star times the partial of n transpose with respect to eta plus J13 star times the partial of n transpose with respect to zeta. That quantity times U2 of the element. Okay, something like that. And we can collectively kind of call all these, we'll call those equations 6. Okay? So you can go on and compute the other 4 strain components in the same fashion. But let me give you a couple notes on this, okay? So here's some notes. Number 1, okay, in the above, all the J star terms and the partial derivatives are functions of space, right? So think of them as functions of x bar, right? Or C and eta bar, or rather C, eta, and zeta. So any computed strain that we're going to have is a continuous field within the element, okay? So strain is a continuous field in the element, okay? That's still a little challenging if we're writing our own code and want to know where we want to report the strain. So we can compute the strain anywhere, but we're going to choose to compute it at the integration points. And why do we do that? Because the integration points are where we have computed the values of the partial derivatives. Okay? So it's because the partial derivatives have already been computed at these points. Okay? Okay, so now that's how we compute strains. How about the stresses? Okay, since this is linear elastic finite element analysis that we're talking about in this section, we can compute the stresses just using Hooke's law. Right, and so in this class, we'll order the stresses as follows. This is just a convention. We'll say the order is sigma 11, sigma 22, sigma 33, sigma 12, sigma 13, sigma 23. Okay, going to be equal to C, the stiffness matrix, times the strain vector, epsilon 11, epsilon 22, epsilon 33, 2 times epsilon 12, right, the engineering shear strain, 2 times epsilon 13, and 2 times epsilon 23. Okay, that's how we're going to define it in this class. We'll call that equation 7. And C here, this is our 6 by 6 symmetric stiffness matrix. So because we've computed the strains at the integration points, the stresses are also going to be computed at the integration points, right? So, okay, so what does that mean? That means that for a fully integrated 8-node brick, right, fully integrated is going to mean that we have 2 integration points per dimension. So 2 times 2 times 2 gives us 8 integration points in a fully integrated 8-node brick, okay? So that means that for an 8-node brick, and this is going to be fully integrated, right, with 8 integration points, we're going to get 8 different stress tensors computed, right? Right, one stress tensor for each integration point. Okay? So, let me just say that the computing of the stresses and strains at the integration point, that's where the solution is going to be the most accurate at those integration points. So that's typically the most accurate, but sometimes we want stresses at the nodes. Now, why might we want that? We might want stresses at the nodes because, for example, those nodes reside on the surface of our part or whatever we're trying to model, and there may be something in contact there or something like that, so that we care about what the stress is at that outer boundary, right? So So let's talk about how we can do that. How can we get stresses at the nodes? So let me just say, while the stresses and strains at integration points are the most accurate, so while these points are the most accurate, sometimes the stresses at the nodes are of more interest. Right? For example, nodes can sit on a surface where the stress is the highest. Okay? So what do we need to do? We need to have a method to extrapolate the stresses that we calculated at the integration points to the nodes. Okay? So let's talk about a methodology for that. Okay, so here's our extrapolation methodology. Okay, so and I'm going to draw I'm just going to draw a 2D element because I know it's not the full 3D, but it'll illustrate the point well. So let's draw a 2D element in its natural coordinates. Okay, something like this. Right? And if this is the center of the element, then this location out here, that is C. And we can come straight down here. That's eta, right? And so we know if it's in natural coordinates that this upper corner point is C equals 1, eta equals 1, right? We also know that the integration points, they're already pre-chosen, so let me mark those. There's our integration points. And those are all at plus or minus 1 over the square root of 3, right? So that integration point is at C equals 1 over the square root of 3, and eta equals 1 over the square root of 3, just for illustration. Okay, so that's what we're looking at. So step 1, we're going to introduce a new set of dimensionless coordinates. And we'll call it R, S, and T. In the example here, since we're only in 2Ds, we'll just have R and S. Okay? And then what we're going to do is we're going to have the values such that, let's say, R equals 1 and S equals 1, you know, at the, let's say the upper right integration point. Okay, so what I mean is that we have this new coordinate system. It sort of forms a box around these integration points. Okay, so this location here that is C equals 1 over root 3 and eta equals 1 over root 3, that is going to become R equals 1 and S equals 1. And so this is my R, right, axis, and then this right along eta is my S axis. So now our integration points run from R equals negative 1 to 1 and S equals negative 1 to 1. Okay? Then what we're going to do is we're going to replace C, eta, and zeta in our interpolation functions with R, S, and T. So for example, if n in the above here was equal to, so if n of C and eta was equal to, let's say in the 2D interpolation function, maybe for the upper right term, this would be 1 plus C, 1 plus eta, right? That would be the interpolation function that corresponds to that point. Then we would just write this then as n of R and S equals 1/4, 1 plus R, 1 plus S. And I also want to go up here and write that this point up here now, C equals 1, eta equals 1, that now is R equals the square root of 3, and S equals the square root of 3. Okay? Okay, so now we have one final step, and that's for any point P. So if I pick a point P, let's pick that point right there, P, right? It could be a node, right? It could be on the nodes, it could be anywhere. But for any point P, in the element or at the node, on the nodes, let's just say, or maybe or on the boundary, right, where P is located at r, s, and t, those coordinates, rs, whatever rs and t coordinates they are, right? Then we can write that sigma of p, the stress at that point, is going to be equal to our interpolation function vector, just like we had, but now it's going to be of r, s, and t, right? Evaluated where r, s, and t is the point p that we care about, right? So that's that vector there, times the stresses corresponding to those integration points that are related to each interpolation function. So we can call these sigma of, and I'm going to put the I on this side for, this tells you it's the stress at the integration point. Okay? So that's all there is to it. It's pretty straightforward. So if I wanted, for example, the stress at this node, I would solve for the interpolation functions evaluated at r equals the square root of 3 and s equals the square root of 3. And I would use the 4 integration point stresses from these integration points in this vector to compute the extrapolation of the stresses from those integration points to that corner. Okay? I want to make one final remark. So hopefully from your intro class you learned this backwards and forwards, but remember that stresses are not continuous across the boundaries of the element, right? So what do we enforce to be continuous? We enforce displacement to be continuous, right? That's why we solve for our displacements at the nodes, right? So the displacements are continuous, but the stresses and strains, which are derivatives of those, are not. So you could extrapolate a stress from one element to the node, and that node could be shared by multiple elements, and you could extrapolate the stress at that node from other elements, and they won't necessarily match up, okay? So let me write that down just as a reminder. So recall that the stress and strain are not continuous across element boundaries. Okay, so as a result, sometimes the difference in the extrapolated values, so let's suppose that you had 3 elements sharing the same node, and you extrapolated the stress from each element back to the same node, and they were 3 different numbers, right? The closeness of those numbers together gives you some measure of the error of your finite element approximation, okay? So let's just say that the difference between the extrapolated stress values at the same node from multiple elements sharing that node can give a measure to the error in the finite element approximation. Okay? So that's the procedure that we use to get stresses at the nodes. That's why we sometimes care about the stresses at the nodes. And sometimes you'll see, even in Abacus, it'll do averaging. So it'll take the projected stresses from each of the elements back to the node, and then it'll do some averaging of those elements based on some weighting that it uses to compute some sort of a nominal stress, and it uses that to build its contour plots. But that's what it's doing, and it's something that now you know how to develop your own algorithm for handling as well.